All right, we're ready to get into the wonderful world of quantifiers. So I've written some sentences here. The first one is, he is taller than that. And I'd like this to be a statement, but we know that a statement needs to have a truth value. And I don't know who he is, and I don't know what that is. So I don't know what the sentence is referring to, so I can't call it a statement yet. But if I am somehow able to quantify the scope of this sentence to tell you what I mean by who and what, I might say, I don't know, Barack Obama is taller than that 2-foot tall fence. Then you know who I'm talking about and what fence I'm talking about, and you can say, all right, now we can tell that this is true or false. And I'm pretty sure Barack Obama is taller than a 2-foot fence. So we can say that this is a true statement. So it has a truth value. Now, we're probably not going to talk a lot more about Barack Obama and linear algebra, whether that makes you happy or sad. There's no value judgments here. But we do run into statements like the one below, like x squared is greater than or equal to x plus 4. And again, I don't have enough information to know what the truth value of this should be. I mean, I could say, for all real numbers, x, and for all real numbers x squared is greater than or equal to x plus 4. And that's false, because if we take the real number 1 squared is 1, and that is not greater than or equal to 5 on the other side. So if I put that quantifier in there and tell you, like, what does x mean, what x's are allowed in this statement, then I can give you a truth value. I could modify this. I could say for all x, let's say greater than or equal to 3, and then I've got 9 on one side and I've got 7 on the others. And I'm pretty sure that if I continue just adding 4, my squares are going to grow faster. So that's a true statement. I'm not going to include a proof of that. There's another type of way that I could quantify this. I could say, I don't know for all r, and I'm like a little too lazy to figure out that it's 3, but I'm pretty sure that there exists an x in the real numbers such that x squared is greater than or equal to x plus 4. And that's also a true statement. So there are a couple of ways that we could quantify this. And when I say a couple, I've lucked out. I actually mean literally 2. We could have a statement that says for all x satisfying some condition, and that's what most of the statements we try to prove look like. Or we could have a statement that says there's some x for which this statement is true. And to demonstrate that, all you need to do is go out and find an x and show that it's true. Say like, yeah, indeed, x equals 3 works. So when I say quantifiers, the ones that I'm talking about for us are these universal and existential quantifiers. So universal means for all, and existential means I'm claiming the existence of something. There exists. So we might write for all real numbers x squared is greater than or equal to 0. That's a true statement. I might say there exists x in R such that, and I use ST as my such that. There's another thing you can use which looks like a little backwards in symbol. Anyway, there exists x in R such that x squared is greater than 2020. I don't know what it is off the top of my head, but I'm pretty sure it's out there. You could also read it as for each. So we might say for each n by n matrix A and each n by n matrix B, A plus B equals B plus A. Or we could say on the other side, the existential side, we could say for some so we could say A squared equals the 0 matrix for some square matrix A. In fact, A equals the 0 matrix would work, but maybe there's some more other ones. And in general, what we're kind of working up to are these things called propositional functions that we modify with quantifiers. So we might have something that looks like for all x in D, D is called our domain of discourse, which really means the place where the things that we're talking about live, right? Discourse, the stuff we're talking about, domain, a place, right? This is the place where we're talking about the stuff. And then we've got some function that involves x. And similarly on this side, our statements are going to look like there exists x in some domain of discourse such that the statement P of x happens. Or sometimes we'd write it as P of x for some x in our domain of discourse. I think usually you see the first formulation, but the second one is also allowed. So let's think about some of our matrix theorems. I'm going to rewrite one of our matrix theorems about addition using this super formal logical notation and everything. So this is theorem 1.1d, which colloquially says every matrix has an additive inverse. Okay, but here's how we would say it in logic. We would say for all A, and our domain of discourse here is a set of m by n matrices, there exists B in the set of m by n matrices such that A plus B equals B plus A equals the 0 matrix. Okay, that doesn't look like the way our theorem is written. And when we're writing mathematics, we use words and not formal logic. But when we're sketching mathematics out on the board or in our notes, we might use some of these formal logic symbols to to make it clear what exactly we're proving, so that we can use some proof techniques that we're going to talk about later. But also just to save space on the page and to be able to write down a lot more in a shorter period of time, right? So this is saying every matrix has an additive inverse. Let's think about what would have happened if we had reversed the quantifiers here. So here's another statement. Notice I'm not calling it a proposition. In mathematics, we reserve proposition to refer to a statement that's true, which is why you'll see proposition and proof all the time. It's really, I think, just so that we don't write down proposition and then say right afterwards it's false, and then you go and you try to cite that proposition as though it were true, and suddenly your math falls apart. So when you see the word proposition in mathematical writing, that refers to a statement that is true. It is a statement because it has a truth value, and in fact the truth value is true. That's a little different than what you would see in a formal logic class. In a formal logic class, a proposition is just the same thing as a statement. It could be false. So just beware reading mathematics that proposition typically means true. Anyway, let's take this statement. Let's reverse our quantifiers. There exists B in the set of m by n matrices such that for all A in the set of m by n matrices, A plus B equals B plus A equals the 0 matrix. The statement is saying something a little bit different. It's saying there's a matrix B that I can add to any matrix to get 0. Here's a matrix B. that can be added to any matrix of the same size to yield the zero matrix. And that's not true. Anytime I try to write down that matrix, I'm going to be able to come up with a matrix that I can add to it that's not going to be zero, right? So this is, this theorem up here is true. We proved it, but this statement is false. There's not a single matrix that can be added to any other matrix to get the matrix, to get the zero matrix. So it's a little tricky when you want to switch your quantifiers. It's not always true. Professor Coburn has an example to illustrate that these are different. And I like this example, but it kind of requires you to know who George Clooney is, and not just that, but how handsome he was about 10 to 15 years ago. So if you need to, pause the video, go look up George Clooney circa 2000, 2005, 2010, and at least for the principle, for the premise of this next example, agree that he's a handsome guy. So there's, you could say, you know, for every person who's attracted to men, there's a really handsome man out there for that person, right? Meaning that our tastes might differ in terms of like which guys we find attractive. The second statement, if I put the existential quantifier first, would be saying there's a guy out there such that everyone who is attracted to men finds this guy attractive. Professor Coburn says that's a true statement because George Clooney's out there. But notice that they're different, right? One of them said you start with, you know, for each person, and then this thing that you're showing exists depends on the person. The other statement says there's somebody out there that works for all people, and that's a really different kind of statement. So careful switching quantifiers. Well, just like with our logical connectives, we might want to know how to negate quantifiers, right? Like if I have a for all statement, what happens if I want to say it's not the case that for all blah, 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 this thing happens? So let's talk a little bit about negating quantifiers. If I want to negate a statement of the form for all x in our domain of discourse, p of x, that is logically equivalent to saying there exists an x in the domain of discourse such that it's not the case that p of x. So let's take an example. We could say, if we want to negate something, we could say, it's not the case that for all x in the set of real numbers, x squared is greater than or equal to x plus 4. And that's equivalent to saying there exists an x in the real numbers such that it's not the case that x squared is greater than or equal to x plus 4. And that we can rewrite because we know how to negate x squared greater than or equal to x plus 4. We could say there exists x in R such that x squared is less than x plus 4. And it's easy to see that this is true once we get it down into this formulation, because you just need to find an x where that works. And so this is true because you can, you know, take x equals 1 or x equals 0, or even x equals 2, I think works, right? Because 2 squared is, yep, that's less than 6. So sometimes it's easier to work with the statement where you kind of move the not as far to the right as you can, because it's just easier to deal with, right? The original statement said, it's not the case that for all x in R, x squared is greater than or equal to x plus 4. Maybe it's just me, but I find that statement harder to work with than there's a real number such that x squared is less than x plus 4. I'm like, okay, I know what I need to do to show that that's true. I just need to find that real number. Okay, we want to be able to negate the existential quantifier as well. So let's see what happens there. If we take the negation of something like there exists X in our domain of discourse such that propositional function of X, that's equivalent to, well, we're going to get a universally quantified statement for all X in our domain of discourse. It is not the case that P of X. Right, and so we switch when we negate an existential quantifier, we get a universal quantifier, and when we negate a universal quantifier, we get an existential quantifier. So let's take an example of this one. I'll give you a matrix example for this one. Let's say it's not the case that there exists a non-zero matrix A such that AIN is equal to the zero matrix. That is logically equivalent to saying for all non-zero matrices A, it is not the case that A times IN is 0. Oops, A times IN. And I know how to negate that statement, right? I need to write this. So for all non-zero matrices A times the identity matrix is not equal to 0. And that statement is easier to see is true than the original. It's not the case that there's a non-zero matrix such that A times the identity matrix is the zero matrix, right? The statement for all non-zero matrices A IN is not equal to Z, that's easier to show is true because the definition of the identity matrix is I multiply it by A and I get A, and A is not 0, right? So like to prove this wouldn't be so bad. We'd say like A times IN is equal to A, which is not 0, by the domain of discourse that we picked, non-zero matrices A. So negation is necessary. We're going to find that we have to negate statements, right? They might be false and we need to show that they're false. So we will have to negate them and do that. And a strategy for working with negations is move the knot as far to the left as possible, or to the right, sorry, I don't know my right from my left, as far to the right as possible. Because that statement is often the easiest statement to work with. That statement will probably be the most straightforward. And you'll see that in the logic packet that I gave you, there are some exercises that ask you to do this. If you're practicing on those and you'd like some solutions, let me know. I've got the solutions to that packet as well. So we've got our, as a wrap up of the logic that we know so far. So just a quick logic wrap up. We talked about connectives. We had not, and, or, implication, and the biconditional. And as a bonus, we talked about tautology and contradiction. And we talked about some laws for dealing with these. Like most of the laws have a statement that says, how do you negate them? And some other logical equivalences that might be helpful. So we've got our connectives, and we talked about quantifiers, which is the logic way of defining, the logical way of defining what are you actually talking about? And so in many of your proofs assignments, you'll notice that your propositions that you're proving, a lot of them look like for all blah, 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 if this, then that, right? So I probably will start writing on as feedback, like, hey, I think you might need a quantifier here, right? Like, what are you actually talking about? And I don't mean that in a snarky way. I mean that in a like, hey, I actually don't know which matrices you're referring to here, right? So, and then we've got the universal quantifier for all and the existential quantifier. There exists. And I'll leave you with a little bit of food for thought. Say for all animals in the set of unicorns, well, maybe I'll make it for each animal in the set of unicorns. The animal has one horn. I would say that this is a true statement. The defining characteristic of a unicorn is that it has one horn. But if I wrote, there exists an animal in the set of unicorns such that the animal has one horn, I would say that statement is false. And the difference is, and I'm sorry if this is a spoiler, there are no unicorns, right? We can't say there exists an animal in the set of unicorns if that set is empty. So that's another slight difference between for all and there exists. For all could be hypothetical, right? You know, if there is a unicorn out there, then it's got one horn, as opposed to there's a unicorn and I know that that unicorn has one horn. Sorry, no unicorns out there. I know, it disappoints me too. All right. Last up in our talk about logic is proof methods, which we will talk about together.